hopeful that everybody else will find us.
Can you take a look at the screen?
Let's see. Loading app. That's weird.
Seems like it's okay.
Yeah, and I don't think you have to be here in that screen in order to like.
Okay.
Yeah. Huh. Let's see. This is the sharing. Yeah, that's pretty normal. Yeah, and it should be shared.
Okay.
And I will be checking, but
Sure.
this is how it usually works out. Okay, guys. I think we can begin. Some of you may have caught Don at the meetup last week at the O'Reilly AI conference. And he was presenting about reinforcement learning and the things that he does with reinforcement learning for his startup. But he'll tell you more about himself and his company.
Sure. So thanks very much, Elena, for inviting me to come and speak to all of you. It's a great pleasure to be here. So about me, so my name is Don Dini. I am, let's see, what am I up to? So I'm the director of AI and automation at a startup, in a nonprofit startup in San Francisco called FoodRev. I'm also with some co-founders who have just started a company called New Cortex. So New Cortex, let's see if I can, if you guys can. Here we are. So this is my company. Myself and a couple of co-founders and a bunch of interns. So we created a company that's all about creating collaborative AI systems to help people solve problems. So if you go to the site, newcortex.ai, there's a video that talks about some of the stuff that we're up to. I won't bore you with it here. But so one of the big partnerships that we've started up doing is working with this, as I mentioned, this nonprofit FoodRev. So FoodRev is a nonprofit that is focused on delivering food to those in need in San Francisco. So right now it's focused in San Francisco, but with the aim of course, expanding to the entire nation. So there's this shocking statistic that that 40% of food which is produced in the United States is thrown away, and that somehow simultaneously 50 million people live in food insecure households. Now, the stuff that is thrown away is for all kinds of reasons. It's things like large restaurants, chains, cafes that all of you have heard of. Simply at the end of the day, they throw away food that they just haven't sold that day, and people will not accept buying it the following day, so they just sort of get rid of it. And this leads to an immense amount of food waste. And so what happens is places such as FoodRev assemble pools of volunteers to pick up food from people who have an excess and who wish to donate, and deliver it to places like low-income housing, places like food banks, places like community centers. And the problem is, when places like FoodRev start to gain a certain amount of success, the logistical problem of simply assigning people from this pool of volunteers to go make pickups and then deliver it to places, and then taking care of an entire outstanding evening's worth of demand starts to become too large of a problem to fit inside of a person's brain. And actually, FoodRev is far from the first person to solve this problem. There are lots of other places that start to similar operations, but what happens is when they grow to a certain size, the people who are dedicated to solving this problem, they just kind of burn out, and then these places go away. So what New Cortex has done is we've created an assistive AI system to help the coordinators at FoodRev scale this to an arbitrarily high degree. So previously, where it was really just like a couple of donors, a couple of volunteers, a couple of people who receive food, now it's hundreds of donors and hundreds of volunteers. And our goal is to expand far beyond there. So we're working on lots and lots more stuff. That's just our partnership with FoodRev. I encourage you to go to the site if you want to hear more. But of course, that is not why we're here. So before New Cortex and before FoodRev, I was at AT&T, where I was a principal data scientist, where I worked on applying AI to different business units at AT&T, where my job essentially was to go to different units and think about how to apply AI to make what they are doing more efficient somehow. So usually by we would aim for something on the order of magnitude of like 100x or 1000x in terms of cost or manpower. Usually what would happen is there's some problem that someone is tasked with facing manually for the past 20, 30 plus years. And just due to the nature of like the increased scale and complexity of the world, that job has become hard to do. And so my job was to go and introduce an AI system to help them to manage the complexity of that problem. So this involved things like finding the cause and diagnosis of problems that you would observe in like a giant nationwide network. So like when someone calls and says, my internet is slow, how do we connect that super high level phenomenological problem to this switch and this rack and this state needs to be replaced? This is a tremendously hard problem. And to solve problems like that, we actually used techniques like deep belief networks, which employ Monte Carlo methods that I'll be talking about today. Wow, that's quite a transition. So, okay, so Monte Carlo methods, I understand that you've been going through the chapters of the deep learning book. So I understand, I went through the chapter on Monte Carlo methods, but I hope you don't mind. I went to the liberty of putting some independent slides together for presenting the same material. I hope you will enjoy it. It's like 40 minutes, something like that. Hopefully you'll find it entertaining. So, okay. Please feel free to stop me with questions at any time. So today, so the reason that people care about this Monte Carlo business, so people use the word Monte Carlo in a couple of different contexts. In this context, in like the machine learning context, typically they are referring to it for the purpose of integration and trying to use computational approaches to perform approximate integration. The reason that people care about that, especially, is for the purpose of performing Bayesian inference. So I'm going to start with some motivating context about what is Bayesian inference and why do people care about it. And then Monte Carlo for integration, especially when it is applied to Bayesian inference. Expanding on that into Markov Chain Monte Carlo, and then talking a bit about some applications. There's going to be a mix of like in the weeds detail and then some high level. So hopefully everyone can find something that is useful. Okay, why do people care about Bayesian inference? So let's suppose that we have a coin, which we strongly suspect is fair. And we flip it a whole bunch of times. And by a whole bunch, I mean 10, so not too many times. And we do this, and what happens is we observe that there are 3 heads and there are 7 tails. And our task as statisticians, as we're trying to, hope that's not a dirty word, is we're trying to, from that data, we suspect, if we hypothesize that this data is produced by a Bernoulli model, meaning with some probability p you have a head, and with probability 1 minus p you have a tail, and that these are independent and identically distributed experiments. Given that model, there is this probability mass function, and then the task is, given the data that we have observed, what is the most appropriate estimate for p, for that probability term? So if you take a statistics class, the first thing that you will learn for solving that problem is the maximum likelihood estimator. And so the way that that works is, let's look at a bunch of data, and we form the likelihood expression here at the top, which, because we have discrete values for a random variable, can be interpreted as the probability that the data that we have observed has occurred. And if you maximize this for the expression p, you get this very simple, easy to understand expression: the number of heads over the total number of trials, right? Super simple. So S stands for the number of successes, or the number of heads. So if we apply that here, we got 3 heads and there's 10 total trials, right? So the probability is 0.3. But is this estimate any good? So maybe if we did this like many times, we did this hundreds of thousands of times or millions of times, and we still got the answer of 0.3, maybe we would be inclined to believe this. But the problem is, all of us have lots and lots of experience flipping coins in our lives. And most of the coins that we have seen do not act this way. And so we have some suspicion. And so essentially what that means is we're arriving with some notion of prior knowledge. And so the way that people have thought of to incorporate and to formalize that prior knowledge is this business of Bayesian inference. And so, as I'm sure all you know, the way that you would perform the same task, you want to infer the value of this parameter p using the method of Bayesian inference, is you form an expression, the posterior expression, which describes what's the PDF that describes the distribution of p given the data that I have seen. And the way that you do this is you form this likelihood expression in which what's the probability that I see this data times a prior. And then we can fill in the values of these things. So for a prior, let's pick some number. Who cares? We'll pick a flat prior. So we'll pick a prior of 1. And then because we have our Bernoulli model, we know precisely how to fill in that likelihood expression right there. And so it evaluates to this expression times 1 because that was the prior. And it turns out that's exactly the same as this distribution, which is well known and loved, called the beta distribution. So the beta distribution looks just like so, in which you have some complicated looking constant. This number here, p to an exponent times 1 minus p to another exponent, that are parameterized by these two parameters, a and b. So in this particular problem, it's precisely a beta distribution if you choose a to be s plus 1, the number of successes plus 1, and b to be n minus s plus 1. And so if you have, so because it's a known distribution, people know precisely what the expectation of this distribution amounts to. And it amounts to s plus 1 over n plus 2. So it's sort of like the maximum likelihood estimator, which is just s over n. But it's like you had 1 additional heads and 1 additional tails. So it's almost the same, slightly different.
Can I ask you to just tilt your machine? Because you're actually not sharing the slides with people online.
Oh, that's terrible.
It's okay. But I'm finding that you're like perfectly positioned. If you tilt it just a little bit up. Yeah.
What do you think?
It's like a 2 seconds late. Hold on. Or like 10 seconds. Just a touch more, and it'll be golden. Like literally. Yep.
All right. All right. So suppose we did exactly the same calculation, but we wanted to mess with the prior, right? So we did this calculation, and the output was a beta distribution. Let's suppose that for our prior, we stick in some arbitrary beta distribution, a and b. We don't specify what a and b are. We just leave them as parameters. So the way that we do this is we have this very same expression. So the likelihood function times the prior. We're going to insert our value for the prior, which is our beta distribution. And if you carry out this calculation, you observe that it's another beta distribution, where the parameters are, instead of just plain old a and b, it's a plus s, and then b plus n minus s. And again, because it's a well-known distribution, we know how to evaluate the expectation of this distribution. And our new estimate for p, everything is exactly the same. We just changed the prior. Our new estimate for p is this expression. So again, very similar to the maximum likelihood estimate of s over n. However, it's as if we observed, prior to arriving, we've observed a heads and b tails. And those numbers a and b are often called hidden counts. So in the multivariate case, this generalizes to the Dirichlet distribution. So let's consider this problem again. You've got 3 heads, you got 7 tails, you observe 10 counts, and you want to solve this problem. I want to estimate the value of p. So let's suppose that you chose values 1 and 1 for a and b, and then you just stuck it into this formula that we just arrived at right here, and we just stick in the appropriate numbers. So we get p is equal to 0.33, which is pretty close to the maximum likelihood estimator. Okay, now let's mess with beta. So the ratio of the hidden counts is the same. They're simply larger in absolute value, so 10 and 10. So now if you do this, The very same formula works out for your estimate for P is 0.43. So it's still pretty close to fair. It took a little bit of, like, you haven't quite dragged it away from fair simply from the skewed amount that you have counted, even though it's precisely the same data. So this gives you an idea that you can sort of dial up and down your amount of skepticism that you have. So in the leftmost graph, this is a graph of the beta distribution. So for beta 1,1, you can see it is the uniform, it is the flat prior. So it's equivalent to f of p equals 1. For 1010, it gets a little bit sharper, so it gets focused on 0.5. And then the scale doesn't describe it super well, but in the rightmost graph, it's beta 50/50. It actually goes higher, all the way up to 8, and it becomes a little sharper. And so as you sort of dial up A and B, it becomes harder and harder to skew it away towards an unfair value of P. You need more data in order to convince the model that it is in fact unfair. And if effectively your skepticism is captured in the sharpness of this prior distribution. And that's why people care about Bayesian inference. It's sort of like maximally flexible. If you felt like it, you could dial this prior all the way down, and it would essentially be equivalent to the maximum likelihood estimator. However, if you have sort of some inexpressible thing that you wanted to account for, some bias that you wanted to take care of, you could do that with an appropriately selected prior. And people do techniques like this to do things like correcting for systematic bias, for example, in sensors, or in which pretty much everything from like a thermometer to any IoT device has some sort of systematic error that has to be removed. So it's sort of this like maximally flexible model, and that's why people care about it. Now, when you want to use Bayesian inference in order to evaluate parameters, pretty much all the time, so as we just did, we had to evaluate this expectation value for this posterior. And pretty much anytime we want to solve any kind of statistical inference problem involving Bayesian inference, it involves having to evaluate an integral involving that posterior. Dramatic pause. Sometimes doing that isn't so easy. So in this expression, really what this is we've got our posterior, and then we've got some complicated function of parameters that we're trying to estimate. And evaluating that might be hard, but not impossible. Sometimes it's actually impossible. So this number here so sometimes this posterior, which you've estimated with some expression, it might not in fact be an analytical expression at all. It could be represented by an algorithm, such as a neural network, or a kernel density estimation, or a decision tree regression, or something like that. It could be something that you cannot apply any sort of analytical closed form method to. What shall we do in that case? So there are lots and lots of numerical methods, but one which has emerged, which is super great because it's really easy to apply. Well, not like really easy, but relatively easier, and has great general application, is what's called Monte Carlo method. So this word Monte Carlo is applied in a few different circumstances, as I mentioned earlier. So one of the places which you might see it is if you have studied reinforcement learning. You see Monte Carlo sometimes applied to policy learning techniques. There it just sort of refers to like the presence of randomization. So for example, if any of you have looked at like the AlphaGo paper, the DeepMind AlphaGo paper, a bunch of references in there refer to Monte Carlo tree search, which prior to AlphaGo was the top of the game for software that played Go. So if we just take a step back and consider this problem more generally, there's some integral we want to evaluate. There's some function h of x, which is some for not too difficult assumptions, we're going to assume is safe to integrate between a and b. And The big idea with Monte Carlo methods is we want to find some way to reformulate that integral to be two things: some function, w of x, and then something here, f of x, which can be interpreted as a distribution, as a probability distribution. And so the idea is that if you do this, then what this integral amounts to, sort of, is an expectation value for just this thing. So the idea is that you found a way to turn that integral into taking an expectation of this function right here, w of x, over that distribution. And so if you can interpret this integral this way, this opens up a very clear way to approximate this number, in which what you do is you just get a whole bunch of sampled numbers from that underlying distribution, f of x, and then with those, you plug them into the number you're trying to take the expectation of, and you average those. So just the sum of those numbers divided by n. And as you get more and more of those numbers, due to the theorem of the law of large numbers, it becomes closer and closer to what the true value of that integral is. Seems magical. Okay, super simple example. Let's suppose you got some integral, x to the power of 3, and you want to evaluate it between 0 and 1. So we're going to apply the very same method. We're going to cast it as these two separate functions, w of x, and then some other function which can be interpreted as a probability distribution of w. So one way to do that is if w of x is x to the power of 3 times 1 minus 0, and then f of x is 1 over 1 minus 0. So that is the probability distribution of a uniform distribution, right, between 1 and 0. And so if we were going to follow this formula, and so if we plug it in to the integral, it takes that form. And so if we were going to follow this formula, so we've changed this from the initial integral to evaluating an expectation value of this thing, x cubed times 1 minus 0, using that underlying distribution, using the uniform distribution. And so in order to do this, all you have to do is take a whole bunch of samples of the uniform distribution between 0 and 1. You plug that in for values of x cubed times 1 minus 0, and then you sum and divide by sum them and divide by the total number. And the more numbers that you collect, the closer it is to what the true value is. So that's a super simple example. Let's look at a slightly more interesting example. So this is everyone's close personal friend, the standard normal distribution. So we have some random variable, z, which we suppose is distributed as a random normal. And what we would like to do is we want to calculate what are the probability that z will take on a value greater than 3. So it's like a CDF, it's 1 minus a CDF. So we're going to follow the same procedure. So the integral we want to evaluate is this integral of f of x from 3 to infinity. And we're going to address this using the very same method. We're going to reformulate it as these two parts, wx and f of x, that can be interpreted as a probability distribution. So one way to do that is if you define wx is 1 if x is greater than 3, and then 0 elsewhere. And f of x is the same standard normal. And so we're going to follow exactly the same procedure. We're going to take samples from the standard normal, as many as we desire. For each one of those samples, we'll plug them in to w of x, sum them, divide by the total number. So if you do this for 100 samples, you get an estimate of 0.0015, which is great. So there's a problem, which I will get to. So there are a bunch of cases where maybe you've succeeded in doing this reformulation. You've got your function w of x, and you've got your distribution f of x. But for some reason, you might want to sample from a different distribution. So that might be because maybe just f of x is just really hard to sample from, and you'd really prefer to sample over something else. Or maybe it would just be really convenient. So let me illustrate what I mean. So let's go back to this example which we just did. We want to find what's the probability that this normally distributed random variable takes on a value greater than 3. So the way that we did it, right, is we sampled a whole bunch of numbers from the standard normal. But the problem is most of those values are less than 3, right? Which means the result is most of those are going to be 0. So if you look at it over here, so the numbers that we're interested in are these over here. And so if you just take your regular sample of a standard normal, by far most of the points are going to come here. So in that sense, most of them are wasted. And so if you want to get a representative data sample of what's here and later, you have to wait like a long time, a very long time. And so what you'd prefer is, even though this is the integral you're evaluating, you'd kind of prefer to sample your data points slightly differently. You'd prefer for them to be sampled closer to where the action is happening. So for example, if you chose, instead of the standard normal, you instead chose one that was centered closer to this cutoff line, like at 4 instead, that would be really great. And so that process is what's called importance sampling, in which you elect to sample from a different distribution, and so you've reformulated your Monte Carlo integral that way. So simple algebra substitution. So instead of f of x, we're going to substitute the one that we want to sample from instead, which is g of x, some distribution that we like. And of course, you have to divide there so that it has no impact. And now you've got your new function here, g of x, which is your new probability distribution. And so now the thing that you're calculating an expectation of is this whole thing right here, wf over g. And so now the task is, instead of the plain old Monte Carlo integration, we're going to calculate samples from this. Those get plugged into this expression. We sum those, divide by the total number. So we can apply that here to our original problem. So that was the original integral that we wanted to do. And we're going to reformulate it as w in terms of wf and g. So we're just going to introduce the new function that we want to sample from, and we'll just plug them in. And then so this, so we'll generate the samples as I just described. So we're generating samples from g of x, and we plug them into that fraction. We get them here. We sum them, divided by n. And we get a number which is slightly different, right? So the original number was 0.0015. Now it is 0.0011, very dramatic. The thing that makes it really a big deal is if you look at the variance of this estimate. So basically, you got this estimate, and let's suppose you did this estimate again. Did you have a question? Yes, sir.
Are you drawing random samples from both f and g? Are you
No, just g.
How are you dividing that by g?
So you sample from g, right? So and you get some number, and then this.
The ratio of b, yeah.
Correct.
Okay.
You got it. Were there any other questions? So so if you went and you evaluated this number I, and you just did it a whole bunch of times, and you take the variance of this. Previously, if you just used the plain old non-importance sampling, your variance was 0.0039, and by using this method, by simply changing the part of the number line that you are sampling from, you have reduced your variance by an order of magnitude. So the confidence in the estimate that you have has dramatically increased, even though the absolute difference of it is not super high. So that's why people care about importance sampling. Yes, sir.
Why did the variance reduce so much?
Yeah, that's a good question. So the reason is, previously, the number of data points that you had around the phenomenon was not very high. It was just it was mostly over here, and essentially the point that you had with which to form an estimate was very small. And by simply changing the part of the number line that you are sampling from, you get much more data around where that the phenomenon is actually occurring, and this leads to local variance. There is a problem, however. Actually, this gentleman was starting to get to it, which is that in order to make this work, you got to form this ratio over here, f over g. And so it turns out that if the tail of g is a smaller tail than f, so basically as you increase x without bound, if f always stays higher than g, or if there exists some point in which after that point f is always higher than g, then this estimate I here can have infinite variance. So basically you can evaluate it once and you go back to evaluate it again, it could be a totally different number. And you basically, you have absolutely no confidence with which, that you can make in what this number is. And so for that reason, although you would like to make G a more friendly distribution, there are restrictions on what you can actually choose it to be. So in general, you want it to be something with thicker tails than what F is. And then in addition to that, you want it to be something that tends to conform to the same shape. Actually, there is a theorem that describes an optimal G that you can choose. But then sampling from that optimal G then becomes super hard. And so it's not actually used in practice. So important sampling is something which is super useful and is very helpful, but can be hard to do in practice. Okay, so just to summarize what we have done. So hopefully I've conveyed, Bayesian inference is super important. People really care about it because it's much, much more flexible than the maximum likelihood estimator, which often can't be trusted. It's sort of like the maximally gullible estimator. And integrals that appear frequently in Bayesian inference are often hard to evaluate. And you can make them easy to evaluate by recasting it as a function, wx, and another function which can be interpreted as a probability distribution. And so you recast this integral as an expectation of w. And then if you do that, you can take samples of f and then evaluate an average of w. So just that alone is super powerful. The only part that's missing is how do you get samples from f? So if f was always something where you knew how to develop samples from it, then we'd be done. But the problem is that very often you have some f that there is an unknown procedure for generating samples of it. Actually, people, a lot of work used to go into generating what those numbers are. So I'm not sure if you guys have seen, there are these books from Rand Corporation that they used to publish where it just had pages and pages of random numbers that you could use as seeds to algorithms like this. There are actually files in some distributions of Linux where they have, they're basically just lists of random numbers, and those numbers have been taken from samples from particle accelerator experiments, which is thought to be like a true source of randomness in the universe. Actually getting your hands on like real random numbers is not so trivial. People have put a lot of thought into it, and sort of the thinking is that due to things like Bell's theorem and quantum mechanics, that there in fact exists some real notion of randomness in the world, and if you can sort of capture that, you can apply it to things such as this. Okay, so sometimes sampling f is tough, and so this approach which has emerged, which is essentially, so it's called Markov Chain Monte Carlo. But the part that we're going to talk about right now is the Markov Chain part, which just plugs into the Monte Carlo part, which you already know, which we just talked about. Often abbreviated as MCMC. So all it is a mechanism for generating data points. And the idea is that if you crank this mechanism sufficiently long, the distribution of those points is guaranteed to settle on whatever f that you have input under certain extremely reasonable assumptions. And that's it. That is what it is. So basically, it's just a thing for generating a whole bunch of points. It's a crank that you can continue to turn, And it's sort of halting problem-esque in the sense that there's nothing that tells you when you're done. So you're sort of constantly creeping up on the desired distribution, F, but there's nothing that tells you like, okay, now it's really good, you may as well stop turning the crank now. You basically just have to eyeball it. You have to eyeball the distribution by looking at histograms, and by essentially what amounts to a subjective evaluation of how much does this look like what the real distribution looks like. But if you have some mechanism by which to evaluate F at some point, either via an algorithm or via some like crazy complicated kernel density estimator that you made up, or anything, some computer program that spits out numbers, this provides a mechanism by which to produce a whole bunch of data points that conforms to that distribution, which you can then use to do Bayesian inference. So I'm going to describe one of the algorithms for arriving at those data points. It's called the Metropolis-Hastings algorithm. So first I'm going to describe it broadly, and then we're going to go into a little bit of more detail into these points. So the first thing that you do is you generate some number. Doesn't matter, who cares? Some number, x0. And in an induction fashion, let's suppose that we have generated I points, or I+1 points here. Okay, now we're at the point where we want to produce a new number. What's the next number we're going to add to this list of numbers? So we propose a candidate value, and I'll describe how we arrive at that number. But we come up with some number, and we propose this number. We then evaluate what's the probability we're going to accept this number. And as you can imagine, that probability is a function of what that value is. If that probability has been met and you accept it, then it becomes the next number in this sequence. If it hasn't been met and you reject it, then you take the previous value, and that becomes the same one. So it's like the next value in the sequence becomes the same as the old value. So a little bit more detail. So step number one, draw up what's called a proposal value for the new value. So you're at this moment, I want a new value. What do I do? So the expression is often denoted Q of y given the previous data point. So you've got your latest point, and your distribution is conditioned on what that previous point was. And so a common choice for what that is a normal distribution, which is centered on what that previous point was. So imagine you're just looking at the last number in the sequence, you got a normal distribution centered there with some variance. And then you're sampling that, and you get some number out the other end. Now, based upon that number, we're going to arrive at what's the probability I want to accept this number. So if your choice for Q there was a normal distribution, then that number becomes the following expression. It's the min of the PDF evaluated at the new number divided by the PDF evaluated at the old number. So essentially, is the new number more extreme or less extreme than what the previous value was? And so the min of that was 1. So as you can imagine, just looking at its properties, if the new number that you proposed was super crazy, so extremely low probability, then this ratio will be small, and so this expression will work out to a low number. And so what we're going to do is with that probability, R, we're going to accept the new number. So if it's a crazy number, it's going to work out to a low probability. And so now there's a low probability you're going to accept the new crazy number. So intuitively, the craziness with which the new number gets proposed is a function of the variance of this distribution, right? So if B becomes really big, you get really big crazy numbers more frequently, which means you select them with lower probability. It's sort of, the B is a number that you tune to determine sort of how daring the sequence of numbers, which is called a chain, a Markov chain. So this is a graph which I stole from this book called All of Statistics by Larry Wasserman, which was demonstrating this phenomenon, which is an amazing book that I recommend all of you read. Actually, I have a list of references at the end of this slide presentation in which that's included. But anyway, so this list of graphs is an illustration of that phenomenon. So Recall B is the standard deviation for the normal distribution. So you got some number that you arrived at, and the question is, what's the new number I'm going to choose? So B determines how crazy essentially is the new number. So if B is really small, what that means is that the new numbers that you propose for the chain are going to be pretty close to what the previous value was. So they're not going to be too crazy, which means that they're going to be accepted with high probability. And that's the highest graph over there. So you're sort of going all over the place because it accepts a new value very readily. In contrast to that, let's look at the other end. B is 10. So you're proposing totally crazy values all the time, but as a result, they're almost never accepted. So what happens is you get this step function-like process. So you got a value here, it proposed a crazy value, was rejected, was rejected, was rejected, but that doesn't happen all the time. Eventually, your crazy value gets accepted, and you jump all the way over here. So you have this phenomenon where it sort of stays flat, but then jumps wildly. What you want is something like in the middle, which is between these two extremes, and that one sort of most faithfully represents what the true distribution is. And if it faithfully represents the true distribution, they say that it mixes well, that the Markov chain, which powers this process, mixes well. And so there's this part at the beginning where it's sort of settling into what the true distribution is, and that process of settling, they call that phase burning in. And so it's very common if you have a package that will generate these sequences for you, they just sort of discard those burn-in factors, and that becomes a parameter that you can set. But the thing is that this is meant to illustrate is that this becomes a hyperparameter, effectively, of your model. What should B be if it's going to be a normal distribution? And if it's not a normal distribution and you pick something else, you still have this problem, but using a different parameter. And there really is no good answer. These are things that you just have to. That is kind of an art. So that was just one type of the Markov chain part of the Markov chain Monte Carlo. There are other algorithms as well. So Gibbs sampling is a more complex version that refers to the case in which you have multiple values. This was when you have just one value. There's a random walk variant of Metropolis. There are different kinds of variants of each of these algorithms, and they're really a function of what is the problem that you are addressing. Okay, I was going to talk about a couple of examples, unless people had questions about anything so far.
Sorry, is there two hyperparameters? Or
So in this particular case, I was just referring to one hyperparameter, which was B, which is what is the variance of this thing that proposes new values. But you don't have to choose a normal distribution. You can choose any kind of distribution, and there are lots of different options for choosing it, in which case you would have other parameters.
So is R hyperparameter?
No, so R is the probability with which you accept the new proposed value. So it's a number that you compute based upon what value came out.
And then you would Bernoulli sample that.
No, so it wouldn't be a Bernoulli sample. So well, yes, you're correct. You're correct. Absolutely. All right. So a couple of applications. I was hoping to put in some more elaborate applications, but I kind of ran out of time, so I thought I would talk about a couple of them. So one of them, which has a special application here, this is really, really useful in deep, large graphical models. So this is actually something where which we faced when I worked at AT&T. So we had problems relating to we had essentially, there was some phenomenon, some alarm which occurred. And from the data, we inferred the presence of this very, very large belief network that surrounded that phenomenon. So these are all these things which might potentially have some kind of influence, either direct or indirect, on this thing that we care about. And as you may or may not be familiar, if you have studied Bayesian belief networks, is if you know the values for a couple of these nodes, so each of these nodes in this massive graph represents some random variable. And if you know the values for a couple of them, there exists a mechanism by which you can calculate the probability distribution for all of the unknown variables. So for example, if you see that the packet transmission metric has gone from 100% throughput to like 75% throughput, there's thousands upon thousands of things which might be the cause of that. So let's suppose that you look at that and you look at one other related thing, like maybe ping transmission for some machine that's nearby, one of the hundreds of thousands of machines that are nearby. So you know that maybe one other value. That leaves a host of thousands of other variables which you have not measured. But the problem is, the goal is, using the power of Bayesian inference, you can estimate important parameters about those things that are unknown. And you cannot evaluate those parameters in an analytical fashion. You have to use some kind of computational method. And in doing that, we use techniques like Markov Chain Monte Carlo. Actually, if you want to learn more about that, I highly, highly recommend this book, which is in the references at the end, which is called Probabilistic Graphical Models by Daphne Kohler and Nir Friedman, which is super good. It's a giant book that's super hard. Okay, next example. This is from a really amazing paper called the Monte Carlo Markov Chain, or the Markov Chain Monte Carlo Revolution by Diaconis. And what is this? Okay, what are we looking at? So what this is they wanted to so the from Shakespeare. So in this case, it was Hamlet. And what they did was they just did a random reassignment. It was like, all right, this letter is going to go to this other letter. So for every letter in the English language, they randomly selected a reassignment, another letter that it should go to. They applied that reassignment to the text and created jumbled text. And so the question is, could you reconstruct what the original text is? And so they did that using a Monte Carlo Markov chain technique. What they did essentially is they trained a Markov chain on the original text of the book, which allows you to determine, essentially, given this word, what is the probability that this other word will appear beside it? Or it could even, I think they did it on a word-by-word basis. I don't think they did it on a letter-by-letter basis. But essentially what that allowed you to do was to evaluate a score of what's the probability I will observe this sequence of characters or the sequence of words together. So what it did was, so in our case, in which we observed a whole bunch of points, and we essentially observed what's the appropriateness of this next point appearing, what they did here is they proposed a remapping. And given that proposed remapping, they evaluated how good would it do, how good would it be if we went with this remapping, and then they accepted or rejected that new remapping according to a probability. So similarly, you sort of follow the schedule of like exploration and sort of this like climbing process of eventually settling upon an optimal remapping that, as you can see, after a few iterations, so the number on the left there is the number of iterations of this process, are reconstructed to a large degree the original text. So these techniques are super, super powerful, and they are used everywhere you see Bayesian inference, which is going to be in the very next chapter. So these are references that I used in order to write this presentation. All of these are really, really amazing texts. The last one is a paper, but all of them are really fantastic. If you read only one, I highly recommend the first one, All Statistics by Larry Wasserman. It's absolutely fantastic. Yeah, and that's all I have. Thank you very much. I hope you enjoyed it.
Does anyone have any questions for Don? I know we have another presentation to follow, but this was a great presentation.
Hopefully it didn't take too much time.
No.
Okay.
What is the connection to deep learning?
Yeah, well, so one of the connections is, so one of the connections is, so as I mentioned, so very frequently, these numbers here, like the this posterior here, is not represented by an expression. It's represented by a deep neural network. So, for example, there are many cases where they talk about it being represented with a restricted Boltzmann machine. And when you have that and you wish to perform some sort of inference based upon this, you can't use just some sort of standard method. You have to use some sort of numerical technique in order to do inference based upon that. Other applications are things like I mentioned, very large graphical models, deep graphical models, in which you have, especially when you have nonlinear functions that are applied between nodes. So it's not simply like a Gaussian that connects one node to the next, but rather some nonlinear operation. Oh yeah, so one place in which it's going to be applied in the next chapter is calculating the value of the so-called partition function, which is used very frequently all over deep learning. Yes, sir.
In your case for deep Bayesian networks, wouldn't you use just something out of the box like OpenBox or infer.net, or have you?
I'm sorry, would you say that again, please?
Like OpenBox, there's a packages that do this box. I don't know. This basically, I think box stands for Bayesian.
But like a software package for doing it. Well, I mean, if someone has written it, then that's great. But like, if I didn't have a piece of software, I got to solve the problem, right? And so if you have a standard software package that addresses the problem, that's fantastic. But it's not very hard to get to a problem that pretty much nobody has arrived at before. Like basically, if you study anything in detail, you arrive at something novel in relatively short order. So it's important to be able to build these solutions. Are there any other questions?
Do you use any packages?
Yeah, sure, absolutely. Yeah. I mean, so at New Cortex, we use lots and lots of Keras and TensorFlow. And then we wrote a lot of libraries, actually, to tell you the truth, for the Bayesian network part. So basically, if you look at what's out there, and so there's lots and lots of stuff out there for doing inference on Bayesian networks, but there isn't a lot of stuff on assembling Bayesian networks from data. And so we wrote a lot of stuff to address that part of the problem. Okay, thank you very much.
Thank you. We can take a little bit of a break and switch over for the next presentation. And yeah, Don is great. She presents a lot. I'm sure if you like Google stuff, he'll come up. Yeah, last week's presentation really was great. Enjoyed it tremendously. Is that everything?
No.
Wait, I think we have one. Okay, it's a very smart machine.
Hey, what's up? I'm Don.
Yeah, Gavin, hi.
Nice to meet you. Sorry, I hope I didn't take too much time.
I don't believe so. Can I steal your connector?
Yeah, absolutely. You mean this one?
Yes.
Go for it.
I cannot find one.
Do you want to stop this, or do you want to keep going?
Let's stop this, and thank you so much.